Hello everyone, I'm Cristian Velazquez. Today I'm going to talk about Gmetrics, processing metrics at Uber scale. A little bit about myself. I work at Uber. I have been at Uber for over 6 years now. I have been on the same team. The team is called Maps Production Engineering Team. But I have been, even though we are a production engineer, I have been doing a lot of work, like efficiency work across the company. Some of those that I can highlight is like garbage collection tuning for Java and Go. Then I also work on distributed load testing. Now I'm focusing mostly on metric emission, so that's kind of the topic for today. And also these base cache solutions and latency tuning. When I'm not at work, I enjoy spending time with my family and playing video games. The agenda that I have for today is first we're going to go and see what is Tally. Then we're going to jump into what is Gmetrics, what are the differences, like the highlights. Then while doing the migration from Tally to Gmetrics, we are going to describe what didn't work as expected, some of the blockers that we had during this migration, how we are doing safe rollout, the impact that Gmetrics has in some services, and the future of Gmetrics. So first of all, what is Tally? So Tally is an open source library developed by Uber that we use to emit metrics. It was released in 2015. It supports different types of reporters. So M3 is the one that we use at Uber, which was built by Uber, but we also support Prometheus reporters. Then Tally supports different types of metrics. So we have counters, gauges, timers, and histograms. And then I want to highlight that we also have code that predates Tally. Like before Tally, we had some other library that we were using to report metrics, which was talking to statsd. And then when we moved to Tally, what we basically did in order to reduce the overhead of migrating all the legacy code was just basically creating wrappers around this old library to speak directly with Tally. Now let's jump into what is Gmetrics. So Gmetrics is the new library for metrics, which is basically a drop-in replacement for Tally. By drop-in replacement, we mean that we are going to still be using the same API that Tally provides, so that we just basically inject this into the code, and then your code is still using the original API. So there are no changes that you need to do. Then we have versions for Java and Go, but today we're only going to focus on the Go version. Both of them are very similar, like all the theory is the same, but obviously the implementation changes a little bit because of how Go and Java handle like maps or things like that. Then some of the highlights of Gmetrics compared to Tally, we are going to look deeply into any of these, so don't worry too much, but let me list them. So we have that it is registryless, it reduces garbage collection overhead, it reduces log contention, reduces drift encoding CPU consumption, and it reduces CPU when emitting metrics. The first point that we are going to describe today is registryless. So in Tally world, whenever you create like a metric, imagine you have this service called API Gateway, then you have an endpoint, and in this case we have like get post endpoint, and then you have like different status codes, and then you add all that information, and then you create the metric with the name calls. So every time that you receive a call to that endpoint with that status code, you increment a counter, right? So imagine that in Tally world, like we start putting more and more metrics into this map, so this map can grow very big. In Gmetrics world, we do a little bit different. So we start with like a root node, which is API Gateway. And as soon as we need to keep adding more information, like, okay, now we get like the endpoint get, we basically create another node, and then we link that to the parent. So this becomes kind of like a graph, right? And your leaf nodes are going to be like the metric name. And eventually you use kind of a report like, okay, we are going to increment this metric. So this approach makes it easier for us because whenever we emit to the M3 reporter, in this case, we basically just like remove all the links. So basically we say, okay, we no longer need the get endpoint, and then we don't need to do any cleanup. The garbage collector is going to do that for us. In Tally world, you actually need to do some cleanup on the map, so it's a little bit more complex doing cleanup there. Then the second point is we reduce garbage collection overhead. So Gmetrics, as a difference of Tally, we basically create like a single asynchronous thread that is going to be processing the metrics. So because we have this, it is easier to do memory management. This is not to say that having multiple threads is makes it impossible to do memory management, but having a single thread makes this very easy. So we are doing our own memory management. So I'm going to put this example where, okay, imagine you receive a metric, it has 10 tags. So because these are tags, you have like key value. So this means you are going to you need 20 objects, right? So in Tally world, that's what is happening. So for this metric, you need those 20 objects. But for Gmetrics, what we do is, as soon as we receive a metric, this metric is going to have like a random order of those tags. So we create the canonical form of this, which is basically ordering the tags and converting this into 3 bytes. And then these 20 tags, we just put them in a single buffer. So we go from 20 objects to a single object. But then we don't stop there. So what we do is we create buffers of same size. So in this case, 32 kilobytes. So imagine this 20 tags combination is like 1 kilobyte on average. So what you actually achieve by doing these two optimizations is that you go from this, because we are seeing like 1 kilobyte, that's 32 multiplied by 20 objects that we need to create in Tally, but then in Gmetrics is a single object. So we save a lot of the overhead that we induce into garbage collection in Tally. Then reduce log contention. So Tally, remember we have this registry, which is a map. We need to synchronize that. So we basically have logs. So most of the time we use a read log. So this read log, we are going to use it whenever we are going to emit to the reporter. We need to go through all the metrics that we have in the map. And then also the first time that you want to update a metric, you need to check if the metric has already been written into that map. And if so, we don't need to acquire the write log. But imagine that, but also for the write log, whenever we need to create a new metric, we need to acquire that, right? So imagine the case where you have like this 100K registry, right? You are going to start the emission to the reporter, then you acquire the write log, and at that time, somebody wants to acquire the write logs to create a new metric, right? So that write needs to wait for the metric emission to happen, which in this case could add like several dozen milliseconds to that specific request. Or we have the other case where you have an expensive write log. So imagine that you need to create this new metric, but remember that we need to create like this canonical form where we order all those tags, and also we need to do some copying and stuff. So if you have way too many tags and they are way too like big in length, they are going to require more memory. So you keep adding more and more to the latency. The way we try, I mean, in Gmetrics world, we also have some log, but we reduce the P99 that we can have in that by having like per proc buffers. So in Go world, you have this concept of Go max procs, which is basically you are going to map, if you have like 4 cores, you are going to create four procs, and then we create 4 buffers, and then each buffer have its own log. So that way, whenever you receive a write operation, we just acquire the log for that write operation, and then we reduce log contention there. And at the same time, these buffers are mainly pointers. So they are not affected by the size of the tags, because what we do is we process everything before the log, and only when we are going to write that pointer, we acquire that write log. We reduce tree encoding. So in Tally world, you are going to have this registry. The key is going to be that canonical form that I was describing, but then the value is going to be some atomic variable that we need to update. In the case of a counter, you just keep incrementing that atomic variable. So when you need to emit to the M3 collector, what we do is, okay, we need to convert this to Tally objects, which is basically when you create the tree file, you do some code generator that it is going to give you like some Go file with how you are going to map from Go to 3 bytes. So then you do this first mapping to Tally objects, and then you do second mapping to thrift bytes. In Gmetrics world, we don't need to do that, because as soon as we receive the metric, if we have not seen it, we do the encoding to thrift directly, and then the subsequent times that we need it, we already have that encoded. The only thing that we need to go and change is the value. So if you have 10 tags, you are basically saving the encoding of those 10 tags. And the last point is we reduce CPU when emitting metrics. Remember that Tally has this registry, so this registry can grow very big. So in Tally world, when you want to emit, what you do is, okay, we first go through all the scopes. The scopes is basically all the combinations of the tags, right? And then each scope can have like different set of counters, timers, gauges, or histograms. And then each histogram, like a histogram, is just basically a counter with additional tags. In this case, it's like the bucket information. Okay, this is going to be from minus infinite to 1 millisecond, then 1 millisecond to 2 milliseconds, and so on. So in this case, what Tally does is, okay, first it needs to go to scope 1 and check every single counter, check if the atomic variable has changed, then go to the timers, then go to the gauges, and finally go to the histogram, but then go to every single bucket in that histogram. So obviously, this iteration can be quite expensive. In Gmetrics, we don't have this problem, because every single time that we emit, we just basically let the garbage collector to collect everything, right? So the next time, everything that we have stored is what we actually need to expose to the entry collector. So there is no like has changed. We know everything has changed. Some things that didn't work as expected. So Gmetrics uses two-level caching. So two-level caching means, remember that we have like we need to order the tags. So the first level is going to receive that unordered tags and then convert it to a canonical representation. And then the second level is going to use that canonical representation to get the actual value of the metric, right? But the problem with this is that because we are following Tally API, the way Tally tags metrics is by receiving a map. And maps have like a complete random order. So what we saw is that a metric with more than 8 tags could generate more than 300,000 permutations, right? So obviously, this generates way too much memory overhead and way too much CPU overhead. So what we decided to do is doing something very similar to what Tally does, which is basically just do insertion sort before getting to the first level cache. But we kind of do it in a more optimized way so that our insertion is even a little bit faster than Tally. Then the second thing that didn't work as expected is, remember that we have this graph structure, so each node is going to have some information. So that information, we basically store it as bytes. So histograms, as I was telling, is a counter with 2 additional tags. One is the bucket and the bucket ID. So what we were doing originally was, okay, whenever we want to record a value for the histogram, we need to, okay, you get the value, then you need to find in the array of buckets where that value belongs to. And then when you have that, you get an index, and then you convert that index to the string representation of that bucket. And obviously, converting to a string is very expensive. So what we do now is, instead of converting at this time, what we do is, okay, we get the index, and then we insert the index directly into the row bytes. And then we only do the conversion to a string when we are going to emit to the entry collector. So that way we reduce, let's imagine you update like a histogram 1,000 times. So originally we needed to do 1,000 time conversions to a string. And now we only do it once, because every single time we just save like the row bytes of that index. And then when we emit, we do the conversion. Some of the blockers that we had is, remember that I was telling you that there is a library before Tally that we created wrappers for that. So the wrapper is not exactly this, but this is kind of the idea. So it basically stores like the scopes in a map. So basically your key is going to be the Tally scope, and then you have like the wrapper structure of that, right? But the problem with this is when you use map Tally scope is an interface. So the key is actually going to use like the memory address, right? But remember that Gmetrics, as soon as we emit to the entry collector, we basically drop the reference. So obviously every single time that you need to reacquire the same scope, Gmetrics is going to give you a new memory address. So this was creating a memory leak. So what we needed to do is have a way so that we can disable this cache and just basically return a new wrapper every single time. And this was even cheaper than having like just kind of getting this value from the map. How we're doing safe rollout. So we have this configuration system called Flipper. You can go and read more about it in the Uber-Eng blog that we have. Basically, whenever we start the application, we check in Flipper if we need to use Tally or Gmetrics because they use the same API. We don't need to do any other changes. And Flipper provides different conditions like region, zone, environment, tier. So basically, if you want to, okay, let's first try Gmetrics on staging. You can do it with environment. Then we can try in Canary. So basically Canary is one zone. Then we can do region. Then we can do all tier 5, all tier 4. And then you can have all those combinations that allow to do safe rollout without having to have like a global blast radius of this. The impact, so this is one service. So you can see on the left so this is how the service starts. So you restart the service and this is P99 throughput per core. So when you start, you are above 260 requests per second, right? But then you can see that over time this degrades. And then as soon as we onboard to Gmetrics, this goes above 300 and then it no longer degrades. And this was happening mainly because in TallyWorld, you start with a very small registry, right? Because you have not created too many metrics, but as they passed, you start accumulating metrics in that registry, which creates GC overhead, like garbage collection overhead. So in Gmetrics world, because we let GC to collect most of the metrics on every emission to the M3 reporter, we don't have this problem. The future for Gmetrics is, remember that I was telling you a little bit about the API. So the API is currently limiting us on like additional optimizations that we can do. So the first one is tag is using like a map string. Having a map is expensive mainly because you need to, like creating the map is like a heap allocation, then you need to generate the hash code of that. They are not coupled together like a slice. So iterating them is expensive. So what we are suggesting now is, okay, we are going to use like a key value per slice, which is going to be the tag pair that you can see at the bottom. And at the same time, the problem with the original API is that if you see tag returns a scope and then counter returns a counter. So this generates a problem where we are creating heap objects that we probably don't need to generate. So by changing this to a function that doesn't return anything, we can do pooling inside. Why we can do pooling with the original implementation is because we are returning those values. We don't know if the user is going to actually, like they could save those values for later use and we don't know. And then we just kind of say, okay, these are free, so you can use them later on, and they are not actually free, right? The user is expecting to have the same value. So this is what we plan to do. And we have seen great results in benchmarks. And that's all I got for today. Thank you, everyone.